The last topic of the first section of our probability unit is conditional probability. And the conditional probability gets back to that question that I proposed last class with the 3 doors, the 2 goats, and the car. Do you remember it? Okay. We had door 1, door 2, door 3. You pick a door, and behind a door, 1 door is a car, and behind 2 doors is a goat. But after you pick a door, they automatically show you another door, and then you have the opportunity to switch or stay. I'm sure there is. What makes something conditional probability is you're given a condition. Now, our product rule for dependent events, events that depend on each other, looks like this. Probability of A and B is first the probability of A, right? If I give you a deck of cards, what is your chances of getting a red card? 1 out of 2, right? Half of them. Yay, I got a red one. That's magic. No. But now, if I got you to pick a red one again, it's not 1 out of 2. Why? Because I've taken a red card out. Your second chance of getting a red card is now 25 out of 51, because I've taken 1 card out. So that's what this second part here stands for. This is the probability of B given that A has already happened. If I've already taken out a red card, it's not 50%. It's not 26 out of 52 anymore. It's now 25 out of 51. Now, rearranging this equation just with simple algebra gives us something called Bayes' formula, which gets this part, probability of B given A, to be the probability of A and B divided by the probability of A. And this is a conditional probability. So you pick door 3. Given that it wasn't door 1, what's the probability it's now door 2 is now 67%. And the problem with conditional probability is it goes against your brain. Your gut probability, you think, I'm good at probability, I can figure things out, like what are the chances of rolling a 6? 1 out of 6 on a dice. Yeah, I got this. Okay, you're feeling really good. Now, okay, here we go. I roll the dice. Ooh. What are the chances I got a 7?
Total?
In total would be 1 out of 6, right? Because there's 6 7s, if we look at our chart, 6 7s out of the 36 possibilities. But now I'm going to tell you 1 of them is a 4. What are the chances I rolled a 7? Okay. Gut feeling, 1 out of 6. Wrong, but it's a perfect gut feeling. I told you 1 of them was a 4, and you want to say that the answer is 1 out of 6, because the other one should be a 3 to get a 7. Okay? It's not. In fact, the numbers, when I tell you what the probability is, you're going to be like, that is so messed up, it doesn't even seem close to being right. The probability is 2 out of 11. Does that seem like it's even reasonable? If it was a multiple choice question on an SAT, you'd be like, I'm not choosing 2 out of 11. That's totally wrong. But it's the right answer. Why is it the right answer? Let's see. We have to go back to, when did we have a dice question? That's not dice. Here's one. This one might be dice. Yes. Okay. Here's the reason. When I rolled, I had a red dice and a white dice. We'll do the white dice is white and the red dice is the yellow one here. Okay? When I told you that one of the numbers was a 4, Did I tell you which one was a 4? Did I tell you it was the white one or the red one? No. I didn't tell you it was the white one or the red one. You just knew one of them was a 4. Whenever we have conditional probability, the condition reduces our sample space. Could I have rolled a 2? Right? Would you put money on that? One of them's a 4. Oh, I think you rolled a 2. Total adds up to 2. No. Right? You moron. One of them's a 4. It can't add up to 2. There's not another dice that has a negative 2 on it. Okay? So when I tell you one of them is a 4, what that did was it's reduced your sample space to this. Everything else, oh yeah, here we go. This all got, these are not even possible anymore. Does that make sense? When I tell you one of them is a 4, those ones all got blacked out. How many are there? How many numbers are left up there? 11. Why not 12? You can't count the 8 twice. And of those 11, how many of them are 7s? 2. Okay? But it's really messing with your brain because you're like, it shouldn't be 2 out of 11. That doesn't seem like any kind of logical number that goes with dice. So conditional probability messes with you this way. So what happens is the condition reduces your sample space because you know some information. And then you have to do favorable over total that way. Yes?
Is there a way for us to figure out what it is above the sample space?
Yes. So that formula that we just rearranged, which is, anybody have any idea what slide we're on? Not on that one. Conditional probability. Oh, this is getting close. There we go. Here it is. If this formula here would help you figure it out. We want to find the probability of rolling a 7. Here's our example that we just did. The probability of rolling a 7 given that one of them was a 4 is equal to the probability of 7 and 4, or 4 and 7, divided by the probability of getting a 4. So our formula, if you looked at your diagram, how many 7s have a 4 out of the 36? 3 and 4 or 4 and 3? 2 out of 36. How many of the numbers out of your 36 have a 4 in them? Those are the ones I circled to begin with. There are 11 out of 36. How do you do a fraction? Divide by fraction, multiply by the reciprocal. 36's go away nicely, and you would get 2 out of 11 that way as well. Even though the numbers feel really wrong. Okay? Now this is a different question if I went like this. Ooh, the red dice is a 4. Now what's the probability I rolled a 7? Now it's 1 out of 6. Because you know for sure only the one column is a 4. And only now the white one has to be. What was really cool on that example is they were both 4s. Okay. All right. Example 1. Of the 53 staff at school, 36 drink tea, 18 drink coffee, and 10 drink neither tea nor coffee. How many staff drink both tea and coffee? This is not a conditional probability question because it's just asked you a straightforward thing. A conditional probability question would give you information. So right now, we draw our our Venn diagram. Okay, the 10, the red 10 is what I could do first. And then we have some options for figuring out the other numbers. If you add up the 36, the 18, and the 10, it will add up to 64. which is more than 53. It's 11 more than 53 because you counted that middle section twice. So you could have found the 11 first as one strategy. Me personally, what I like to do is I like to think of the whole green circle is 36, right? 36 plus 10 makes 46. This section that's left, that's the black 7, has to add up to 53. That's how I like to figure out sections. And then after that, everything else works out perfectly. So how many staff drink both tea and coffee? That's the 11. Okay? A person is chosen at random. Find the probability, drinks tea but not coffee. Well, that's our 25 person here out of 53. Part B is a conditional probability question. They tell you that they're a tea drinker. What's the probability they drink coffee as well? Why is this not 11 out of 53? As soon as they tell us it's a tea drinker, how many people are we thinking about? We're just thinking about the 36. How many drink coffee out of those 36? 11. So we can find the answer directly without the use of our formula. But if we wanted to use our formula, probability of a coffee drinker given they're a tea drinker, well, coffee and tea, that's our 11 out of 30 out of 53 people total. Divided by the probability of a tea drinker, that's our 36 out of 53. Fraction divide by fraction, multiply, simplify, you'd get the same answer. So a conditional probability question is easy if you can right away tell how the sample size has been reduced. In this case, when they give us it's a tea drinker, it's easy to see that there's only 36 people. And so to say 11 out of 36 directly from the Venn diagram, no formula is necessary. But there's going to be some situations where it's not easy to reduce your sample size, or you don't even know how big your sample size is, so then we will need to use our formula. If he is a tea drinker, he does not drink coffee. Well, you know it's the 36. There's 25 that don't drink coffee. 25 out of 36. Again, B and C are conditional probability because you're given a condition that reduces the size of your sample size. Instead of having to worry about all 53 people, right? Yeah. You can reduce it to that. So here's our next example. Again, these first ones are ones that you do not need to use the formula. You can just use your logic. Think about how does the condition reduce your sample size, and then favorable over total. If it's a black card, how many black cards are there in the deck? 26. So what is the chance that you get the ace of spades? 1 out of 26. Okay? So your logic flows nicely from there. Okay? Want to use your formula? You can. Probability of ace of spades given that it's black. Well, how many ace of spades and black are there? Well, there's just the one out of all 52 cards. And then, how many black ones? 26 out of 52. Multiply by the reciprocal and simplify. Same answer. In this example, I would hope you would just write down the answer. Okay? It's easy enough to reduce the sample space. Here is a good question that is not easy to figure out the sample space, and the formula is very helpful. Okay? A manufacturer has 3 machines, and these machines make kitchen cabinets for them. Machine 1 is the fastest. It produces 40% of the cabinets. Machine 2, 25%. It's probably the oldest one, doesn't work as fast. and machine 3 does the rest. Now machine 1, the fastest one, is the newest one, but it still makes mistakes. This is not a very good, all of these, this is quite high. If you own this company, you'd be quite disappointed. 8% of them are defective. The old one, 15% are defective. And the last one, 10% are defective. So you randomly choose a cabinet, and you know it's defective. What are the chances it came from machine 3? Okay. Machine 3 makes 35% of them, but it only does 10% defective. We can set up a tree diagram for what's happening here. First of all, it either comes out of machine 1, 2, or 3, and we know the percentages from there. And then afterwards, it's either defective or not defective. That's ND. Try to choose letters that make sense. Or the first time it might be good to write defective and not defective and then use D and ND instead of good and bad. You could do that too, as long as you define it. Because what could also G and B stand for? The B could be the best, and the G could be gross. Yeah, it's like, ooh, that cabinet just... Ugh. Yes? For the N branches, because it's either defective, which is 8%, that means 92% would be good, or not defective. So what is the probability it came from machine 3? Well, we want probability machine 3 given that it was defective. We do the probability of both of them together over the probability it was defective. Machine 3 and defective is just this branch. 3 and defective, 0.35 times 0.1. The probability of it being defective could come in 3 different cases. Could have been a defective 1, through 2, or through 3. So here we're only using the formula. Plug it into our calculator. You're going to get 33.5%. Notice what we don't have in this question is the sample size in total. Right? When I did the question with the ace of spades, you know that there's 52 cards in a deck. And when I tell you when I give you the condition it's black, you knew that that got reduced to 26. What we don't know here is how many cabinets are we talking about? And if it's defective, how many is it now? So another strategy that sometimes people use in a question like this is they choose a number. So here, pick a number, sometimes something fairly large. Let's say we make 10,000 cabinets. Okay, I can make a chart here. It either comes out of machine 1, machine 2, or machine 3, right? And they're either defective or not defective. And we can figure out totals here. And totals down here. Wow, that looks like a really good spelling of totals. Beautiful. Nice. So if you had 10,000 cabinets, and we know that machine 1 made what percentage? 40? 40% of 10,000, that'd be 4,000 there. Okay, machine 2 was 25%, 2,500 there, 3,500 there. That adds up to a total of 10,000 cabinets. Okay. Machine 1, 8% were defective. 8% of 4,000, that would be what, 320? And that would leave you with 3,680 not defective ones. Okay, machine 2 was 10% defective. 15, oh, machine 2 is a bad one, right? 15% is 375. Sorry, my mental math might be off here. 2,500 minus 375, 2125. Okay, this one was the 10%, 350 and 3150. So the total amount of defective ones out of 10,000 cabinets, add these up, we get 1,045. That's our new sample space, given that it's defective. If we were thinking about 10,000 cabinets, the numbers that we were told, the percentage that we were told, now we're only thinking about 1,045 cabinets. What are the chances it came from machine 3? 350. If I do 350 divided by 1,045, do I get the 33.5% that my other number was? Yes. It works out perfectly. Okay? Now I chose a large number, so all of my numbers turned out to be whole numbers. Right? If you made 10 cabinets, you'd have like decimals. Your probabilities would still work, and the answers would still work, but it wouldn't make physical sense. It's like, oh, I made 3.8 defective cabinets today. It doesn't really make sense. Last example, another one where using a tree diagram and the formula will work. The hardest part about conditional probability questions is just recognizing them as conditional probability questions, because the formula and solving the formula is really quite easy. Toby the tennis player, if he gets his first serve in, 75% chance he's going to win the point. Second serve, it's like my second serve where I just lob it over, and it's not looking good after that. So it's only a 45% chance of him winning with his second serve. He can get his first serve in 3 out of 5 times, and second serve 3 out of 4 times. Find the probability that the next time it's Toby's turn to serve that he wins the point. Okay? So let's draw a tree diagram. He serves first serve. Obviously that would come before the second serve. Thank you. First serve, it's either in or out. Agreed? What are his chances of getting his first serve in? 3 out of 5. And a 2 out of 5 chance of serving it out. If he serves it in, he's either going to win or lose. Correct? What is his chances of winning? 75%, 3 out of 4. Losing, 1 out of 4. What happens if he serves his first serve out? He serves a second serve. It's either in or out. His second serve, 3 out of 4 for getting it in, 1 out of 4 for getting it out. What happens if he serves his second serve out? He loses. Right? 2 serves out, he loses. If he serves it in, he still has a chance to win or lose. Chances of winning now are 45% and a 55% chance of losing. So we have to take the situation and figure out a tree diagram. find the probability that the next time it's Toby's turn to serve that he wins. Let's take out our highlighter here. How can he win? He can win this way, or he can win, ooh, I like that way. So there's two cases. We can write the probability of winning would equal case 1, 3/5 times 3/4 plus the other way of winning would be 2/5 times 3/4 times 0.45. So here, just analyzing the situation and creating your tree diagram, that's the hard part. Calculating, given that Toby wins, so we want to do probability of first serve given that he wins. According to our formula for conditional probability, it's your first serve and a win over the probability of the win. And the IB likes to do this for conditional probability. They ask you the conditional probability in part B because in part A you figured out part of it. Okay? Did anyone figure out the number for this on their calculator? No. Right? First serve and win is 9 out of 20. We would divide by the probability of the win that we got to begin with to find the total percentage. So I'll let you calculate those on your calculator and put them in.